Hello AP Chemistry and welcome to 17.2 Buffered Solutions. I feel like in this unit I have said it a lot, but this is the section where it all comes together. And I do mean all, right, in that everything we talked about in 16, right, the concept of is it a strong acid, weak acid, strong base, weak base, the salts, right? All of that comes together here, right? So if any of those tidbits are fuzzy, right, go back and review that stuff from chapter 16. All right, so for starters, it is so important that the first thing you do every time you approach a problem is you figure out what is in the solution before you do any work, okay? Because that's going to determine how much work you have to do to solve the problem at hand, right? Because, for example, if it's a strong acid, right, or even a strong base, right, that means the solution is very simple, right? It all dissociates, it all reacts, and the math gets very simple, right? In that the strong acid concentration or strong base concentration reflects the concentration of hydronium and or hydroxide in the solution, right? Super simple, right? If it just happens to be a weak acid or a weak base, then the math is, equilibrium based, right? And you should probably think about a Rice table as part of your work, right? And how much is produced, right? And then if it asks about pH, you'd have to work from there, meaning we have to know our K values for the respective acids and bases, right, that are involved. Then we have a further scenario, right, where we have a weak acid, right, and its conjugate, right, or a weak base and its conjugate, yes? In either of these two scenarios, that means we have a buffer system, and we have to be even more thoughtful about the work that we're going to do, right? And then obviously, any of these scenarios could be more thoughtful if we then take that scenario and then add something to it, right? So anyway, make sure you assess what's present, right? Obviously, these scenarios constitute buffers, and it must be, right, a weak acid and its conjugate specifically, right? Because the whole point of a buffer, right, is that the weak acid acts as an acid, the conjugate acts as a base, and because they are the same, right, and going back to that whole, common ion effect, they don't consume each other, right? They just exist in the solution together, which means that now we have an acid and a base coexisting in a solution, which means that added acid or base can be neutralized, yes? All right, the essence of a buffer. So, how a buffer works, right? Going back to things we should know. So here is our initial buffered solution, right? And in this case, we're talking about an acid buffer that contains equal concentrations of HF and F minus, right? Going back to the fact again, right, where if I have the concentrate, oh, that color's terrible. If I have HF and water, right, in solution, I'm going to have F minus and H3O plus, right? But if I have a significant amount of F minus, HF is not going to dissociate significantly, so I'm just going to have a boatload of both of those two things hanging out in the solution. This acting as an acid, this acting as a base, right? And so we can add those labels down here even, right? So this is our acid component, right? And this is our base component. So if we were to add some acid to the solution, right? And so we're talking adding a strong acid, right? Then that acid is going to react with the base, right? So we will have consumed some of this. We will produce some of this, right? And we could write a reaction for that, right? So we have our F minus. Oh, yep, it's down here. So F minus plus H plus gives us some HF, right? Which means we consume some of this and produce some of this, right? And that's how it neutralizes H plus. But you'll see that the total, the ratio of HF to F minus doesn't change significantly, right? And if we were to go in the opposite direction, right? If we were to add hydroxide ion, that's a base, so it will consume some of the acid, right? So it consumes some acid, it produces some of the base, right? But again, the overall concentration, the ratio between HF and F minus don't change significantly, right? Good, makes sense. Make sure you understand that and make sure you can always think through that, right? In that a buffer contains an acid and a base that don't consume each other, so that when we add strong acid or strong base, right, those can be neutralized, yes? All right, so buffer basics. I should have come up with a better word than that, right? But for an acidic buffer, it has to be a weak acid, right? And its conjugate base. Must be, right? Now, we must have both of those things in solution. And if we think about what that's going to look like, right, we have our weak acid plus water is going to give us A minus and H3O plus, right? Which then we'd have a Ka expression for that, right? Which means A minus H3O plus over weak acid, right? And then your book goes through this derivation, which is really important, and it can be very useful for buffers, right? So hopefully at this point you just have this expression memorized, right? This is just what a Ka expression looks like, right? So if we were to do a tiny bit of tweaking, we could bring up that weak acid and say Ka times weak acid, right? And then divide that by my A minus is actually going to give us our H3O plus, yes? In that I can solve for the concentration of hydronium ion right by this. And the neat thing here is that it allows us to look at these concentrations in a slightly different relationship, right? In that the amount of H3O plus, right, first of all, when weak acid equals A minus, what's true? Right, Ka is equal to H3O plus, yes? When Wa equals A minus, Ka is equal to H3O plus, yes? Does that make sense, right? Which is why, so for example, in this particular scenario, because HF and F minus are the same, I know that in this initial buffered solution, the H3O plus concentration is equal to whatever the Ka value is for hydrofluoric acid. Yes, does that make sense? All right, now the other thing to take note of, right, is that Ka is a constant, right? Right, that's the whole point, right? It's the acid dissociation constant. Since Ka is a constant, what that also means is that the hydronium ion concentration basically reflects the ratio of weak acid to conjugate base, yes? Because Ka is a constant, the hydronium ion concentration reflects the relationship between the concentration of Wa and A minus, all right? So then, the significance here, right, is that if these relationships don't change significantly, right, in that if this goes up a little, this goes down a little, right, the concentration doesn't, the relationship or the ratio doesn't change much, neither will H3O plus. Yes, does that make sense? Okay, so then if we look at it on the flip side with the basic buffer, right, we need to have a weak base, right, and its conjugate, right, its conjugate acid, that's what it needs to be composed of, right, and so the way we're going to symbolize weak base is just with a, let's use a B, base plus H2O is going to give us a protonated base, right, plus OH minus, yes? All right, so then if we start here, then we could write a Kb expression, right, which is going to say protonated base, hydroxide ion, over base, yes? And that's our Kb expression, and again, hopefully you've just memorized that, otherwise you can always just work your way there, right? And then we can do the exact same scenario, right, where I can say Kb times my initial base concentration over Hb is equal to my hydroxide ion concentration, right? Which gives us the same scenario, right? Where again, Kb is a constant, right? If my Hb and my B are equal, right? Or if my base and its conjugate concentrations are equal, then your Kb will reflect your hydroxide ion concentration, right? And again, as the ratio of B and Hb plus do not change significantly, right? Neither will the hydroxide ion concentration and neither will the pH, right? Now, the neat thing is, right, that this can be written from the point of view of the base, or it can just as well be written from the point of view of the acid, right? And this is why I think things start to get a little bit complicated for people, is because you can do it either way, you just need to be attentive to what you're doing, right? There is also the scenario where we could just do it from the point of view of the acid, right? So let's just, I know that's going to overlay terribly, right? But let's just, you know what, let's just shrink it down a little bit and move it over here, okay? Now, let's say that we wanted to do it from the acid point of view. So we're still talking about a basic buffer, right? Which is still going to be composed of a, oops, We're still talking about a basic buffer, so it's still going to be composed of a weak base, right, and its conjugate acid. But let's do it from the point of view of the conjugate acid, right? So let's say we have Hb plus H2O, right, gives us what? Gives us our base plus H3O plus, right? Which means that now if we're talking about it from the point of view of this is a Ka expression, right? We might have to use Kw to figure out what the Ka is for that conjugate, right? But now we have flipped it so that way we can look at it all from the same point of view. Yes? Does that make sense? Right? Even though it's a basic buffer, right, it'll have a basic pH, but we can analyze all buffers the same way. We just have to start from the right thing, right? So here, for an acid, obviously it's really sensible, right? You would just obviously start your hydrolysis and everything else that goes with it, right? With your weak acid, right? In a buffer, our tendency would be to start from the base, right, in a basic buffer, right? But if we start from the acid, that means that, or the conjugate acid, we can look at the math the exact same way, which may be less confusing. I don't know, maybe it's more, I don't know. Look at these methods, see how you feel about them. If you have some questions about figuring out what works best for you, come see me sooner than later, and we can try to help you find the best method. All right, thank you for listening, be good, and no worries. Lots of practice coming up next. Okay, be good.